In the last lecture, we were discussing the constitution of the nucleus of an atom. We found that the knowledge existing at that time could not explain the structure of the helium nucleus. To explain that, Rutherford made a suggestion that inside the helium nucleus, electrons and proton, one electron, one proton, they form a pair. So that there are two such pairs and only 2 units of charge is left inside the nucleus. However, the existence of electrons in the nucleus was disallowed by the uncertainty principle of Heisenberg. Then we explained what the uncertainty principle is all about. It told us that the product of the uncertainty in the position and the uncertainty in the momentum is equal to h cross. X and p and E and T are known as complementarity pairs in quantum mechanics, and therefore, delta x delta p equal to h cross as well as delta E into delta t is equal to h cross. This is what we did in the last lecture. Now, in this lecture we resume our story of the structure of the nucleus. Since precise knowledge of a complementarity pair of variables is prohibited by uncertainty principles, quantities like their position, momenta, energy and times can only be known in terms of their probabilities. The first thing the uncertainty principle did was to point out a fundamental flaw in the Bohr model of the atom. Bohr model said that electrons exist in orbits around the nucleus. Now, you can plot an orbit only if you know precisely the position and momentum of the particle at the same time. Now, this became impossible because of the uncertainty principle, and therefore, the existence of orbits, definite orbits, that also became the impossible, and therefore, now we talk only of clouds of electrons which are orbiting the nucleus. The Bohr atom has been modified to this extent. So, therefore, instead of definite orbits, we can talk only of probability clouds of electrons. For example, instead of saying that an electron is present at point x, it will be correct to state that it is probable that the electron is located at x. Without the uncertainty principle, it would not be possible to explain many phenomena in physics, such as tunneling, for example. We shall come across this later. Radioactivity, again we shall study later, and even the structure of the atom was difficult to be explained if we accepted the uncertainty principle. Once we accept the uncertainty principle, then it became possible to explain all these things. The uncertainty principle has also found a prominent place in modern philosophy. You see, earlier Newton's theory said that we can determine precisely the position and momentum of a particle. That became impossible in quantum mechanics. Therefore, there is now a new school of philosophy known as indeterministic philosophy, that nothing is determined completely. Since electron cannot be present in the nucleus due to the uncertainty principle, the suggestion of Rutherford that one proton and one electron they can form pairs was not acceptable. Then how can one explain the structure of the helium nucleus? Rutherford proposed a very ingenious solution. He said that the nucleus contains particles which have approximately the same mass as the protons, but carry no charge. That means, these particles are neutral. Because of the fact that these particles are neutral, they came to be known as neutrons. These particles were ultimately discovered in 1932, but the suggestion was made much earlier by Rutherford. So, let us now concentrate on the discovery of the neutron. This is another very interesting story. The discovery of neutron is an interesting story worth telling. Several years after Rutherford predicted that the existence of these particles, that such particles exist, two German physicists by the names of Bothe and Becker bombarded beryllium with alpha particles emitted by a polonium source. Have you ever wondered how many times we shall involve alpha particles in various discoveries? They found that penetrating and electrically neutral radiation was emitted by beryllium when bombarded by alpha particles. They thought that this emitted radiation was gamma radiation. In 1932, Irene Joliot-Curie, daughter of famous Marie Curie, and her husband of Irene, Frederick Joliot-Curie, they decided to study this phenomenon. They wanted to know what is the nature of this penetrating radiation which is emitted when beryllium atoms are bombarded by the alpha particles. They found that the target emitted protons. They thought that the photons of the supposed gamma radiation were responsible for the emission of protons. They did discover the emission of protons, but they thought it was gamma radiation which was responsible for the emission of protons, much like the emission of electrons by the action of photons in Compton effect. In Compton effect is this, that if we have a radiation falling on a target, then this radiation is scattered, the energy of this scattered radiation is lower than this energy, and the difference in the energy is given to an electron, which then moves in this direction with that energy, the difference of these two. This is Compton effect, and they thought that the protons which were emitted by beryllium atoms were also forced by the gamma radiation. They did not know at that time that gamma rays did not have enough energy to emit the protons from the beryllium particles. Anyway, so that was the story till that time. But when news of this experiment reached Rutherford, he suggested to his associate James Chadwick to perform the experiment afresh. What was the experiment? Can I remind you that we have alpha particles falling on a target, say beryllium atoms, and protons are emitted, and till that time the idea was that these protons are emitted because of the gamma rays falling on these particles. Now, Chadwick was given the task of performing these experiments afresh. Chadwick used not only hydrogen as target of the beryllium emission, he also used atoms of other light elements like helium and nitrogen. By carefully measuring the recoil energy of the emitted charged particles, protons in this case, Chadwick was able to show that the emission from beryllium contains a neutral particle whose mass is almost the same as that of the proton. This confirmed the existence of the neutron, and Chadwick was awarded Nobel Prize in 1935 for this discovery. What was his apparatus? You see, alpha particles emitted by a polonium source, they fall on the beryllium target. This beryllium target emits neutrons, which was earlier thought to be gamma rays by Joliot-Curie and others. They were actually neutrons, and these neutrons, when they fall on the paraffin target, the paraffin target is basically hydrogen, and then we get the emission of protons. So, that was the experiment of Chadwick. Earlier, this was the missing link. They thought that this emission was gamma rays, and gamma rays give rise to the emission of protons. And here is another peek into how science works. It is interesting that Joliot-Curie had the right idea for the discovery of the neutron. Both husband wife team, they had the right idea, but they misinterpreted the results of their experiment, and they missed the discovery of neutron and thereby the Nobel Prize. It is another matter that they won the Nobel Prize in 1935 for the discovery of artificial radioactivity, but at that time they missed it. So, one problem however still remained. You see, now we have discovered the neutrons. So, one can say the nucleus consists of neutrons and protons. So, that in the helium nucleus, for example, there are 2 neutrons and 2 protons, that is 2 units of charge and 4 units of mass, and there are 2 electrons, which the charge of the electrons and the charge of the protons in the nucleus, they make the atom overall neutral. That was the picture. Now, one problem however still remained. How do the protons remain confined in the nucleus despite their mutual repulsion due to Coulomb forces? You see, protons carry charge, and the Coulomb's law says that if the two charges are similar, they would be repelled. There will be force of repulsion between them. So, how do you confine the protons then in the nucleus? There are two protons, for example, in the helium nucleus, and if they pull apart, then the atom becomes unstable, the nucleus becomes unstable. How do you overcome this problem? The presence of neutrons helped to separate the protons and thereby reduce the repulsive force between them. Even then, the repulsive force is sufficiently strong to send protons flying away from each other. The resolution of this problem had to wait for the discovery of another force called the strong force or the strong reaction, as people like to call it. So, it is what is discovery of the strong force that was able to explain the stability of the nucleus when there are charges which repel one another. What is the strong force? The strong force is one of the four fundamental forces of nature, along with gravitational force, electromagnetic force, and the weak force. There are four forces. In fact, when we did forces, I did point out that these are the four fundamental forces: the strong force, the gravitational force, electromagnetic force, and the weak force. These four are the fundamental forces of nature. The strong force is the strongest of all fundamental forces. It is about 100 times, in fact 137 times the stronger than the electromagnetic force. And electromagnetic force, is many orders of magnitude stronger than the gravitational force. The strong force is not the usual inverse square law force. So far, we know Coulomb force, for example, which decreases as 1 by r squared, gravitational force which decreases as 1 by r squared. This force, the strong force, is not a force which decreases inversely as the square of the distance. That is why this force is called a short range force, because the force comes into play only when the distance is very small, of the order of 10 to the power minus 15 meters, that is 1 Fermi. So, its range is very short. Another property of the strong interaction is that at very short distances, at a fraction of an Fm of a Fermi, the force is strongly repulsive. I have a graph here, I will show you this. You see, this is strong force, and when the distance is very short, then this becomes repulsive. At distances larger than this, it is an attractive force, and then it suddenly becomes repulsive force. So, what is this strong force? It is now known that protons and neutrons, collectively called nucleons, are not elementary particles. They themselves are not elementary. That means, they can be broken into other elementary particles, and those elementary particles are quarks. So, proton and neutron consist of 3 quarks each. The quarks interact with one another through the strong force, which results from the exchange of gluons between them. You see, if you have one quark here, one quark here, then they emit, reabsorb these gluons, and that is responsible for the force between them. The force of very strong force of attraction between the quarks. Gluons keep the quarks attracted to one another and keep them confined within protons and neutrons. Proton has 3 quarks and neutron also has 3 quarks. The nature of the quarks in them is different, but both of them have 3 quarks each, and the strong force between quarks keeps them tied or inside the neutrons and protons. You see, when nucleons, which each nucleon, each proton and neutron consists of 3 quarks. So, when they approach each other, a neutron for example, or a proton approaches another proton or another neutron, then these quarks inside these particles, they feel the force due to the other quarks. Let me show you here. These are the 4 nucleons, and there are quarks inside them. and they are within a very short distance between them is very small, say of the order of a Fermi, then the strong force acts between these quarks, this one, this one, this one, this one, this all types of pairs of quarks, they exert forces on one another. So, what happens? The resultant of all these forces is the force felt by the nucleons. Interaction between quarks in the nucleons takes place through the exchange of gluons. Exchange of a gluon between quarks is like a ball being tossed back and forth between two players. As I said, if there are two quarks, then they exchange continuously, keep on emitting and absorbing gluons, and that is how they feel the force of one another. So, the residual force is the force that acts between nucleons. All these, you can see these vectors in red from one quark to the other, and if you take the resultant or the residual, then that residual force is the force between nucleons. The current understanding is that the strong force is primarily the interaction between quarks, as I have been saying, and the force between the nucleons, the so called nuclear force, is the residual strong force. Let me explain again what is residual. You see, these are quarks contained inside the nucleons, and they interact in all sorts of ways. And if you take now the resultant of these, or the residual of all these forces, that is the force that acts between nucleons, and this is called the nuclear force, and it is also known as the residual strong force. The residual strong force between nucleons is generated through the exchange of pi mesons or pions. Mesons are particles which have masses 200 to 300 times the mass of an electron, and it is intermediate between the baryons like nucleons and leptons. Leptons are electrons. So, between baryons and leptons, that is between masses like protons, neutrons, and masses like electrons, there are intermediate particles which have masses about 200 to 300 times the mass of the electron. Remember, mass of the neutron or proton is 1800 times the mass of the electron. So, these are intermediate mass particles, that is why they are called mesons. Mesons are intermediate mass particles, and it is the exchange of mesons between the nucleons that results in the residual strong force. So, at a distance of the order of 10 to the power minus 15 meters, that is 1 Fermi, the nuclear force is strong enough to overcome the barrier created by the Coulomb repulsion. We started with this, that if there is Coulomb repulsion between protons, how do they exist together? Now, we have found that the Coulomb repulsion is overcome by the strong nuclear force, a strong residual force. Because of the short range nature of the strong nuclear force, only nearest few neighbors can interact and overcome repulsion due to Coulomb forces. Nucleon outside this short range can still experience Coulomb forces. The idea is that only the nearby protons, they can feel the strong force, and their repulsion is therefore overcome by the strong force. The protons which are at a larger distance do not feel this kind of force. So, therefore, it says that they still can feel repulsion, and that is why the nuclei with a large number of nucleons tend to be unstable, because near ones can feel the strong force, but which are at a larger distance, they cannot feel the strong force, and therefore, the force of repulsion between them is still there, which can disrupt the nucleus. This I have explained to you already, that at a very short distance the nuclear force or the strong force becomes repulsive. At slightly larger distances, say 1 Fermi, 2 Fermi, this is an attractive force. And here is the comparison between the Coulomb force and the strong force. Strong force, as I told you, is more than 100 times stronger than the electromagnetic force. And here is how the nucleons interact. At very short distances, the strong nuclear force is able to overcome the Coulomb potential barrier between the nucleons. You see, this Coulomb repulsion can be pictured as a barrier between the two protons. So, in the case of nucleons, the exchange particles are pi mesons or pions. nucleons give off and reabsorb these particles when the distance between them is 1 Fermi. As I have been telling you, these are the two nucleons and they exchange continuously, absorbing, re-emitting, absorbing, re-emitting, continuously exchange pi mesons between them, and that is the reason that there is strong force between them. The strong force is due to the emission, reabsorption of the pi mesons between the two nucleons. These mesons are called virtual mesons because they exist in violation of the law of conservation of energy for extremely short times. Interesting, you see, the existence of mesons is against the law of conservation of energy, because where do they come from? You cannot explain from the law of conservation of energy. Is the law of conservation of energy violated? Yes, but for very short times. Again, because of uncertainty principle. You remember, delta E times delta T is equal to h cross. So, if there is any fluctuation in energy, say delta E, then it can exist for a time delta T, which is equal to h cross by delta E. So, that is what it means, that these mesons are virtual mesons because they exist in violation of the law of conservation of energy for extremely short times, allowed by the uncertainty principle. I told you when we were discussing uncertainty principle that there are many things in physics which cannot be explained otherwise. You have to invoke uncertainty principle, and that is what we are doing here. These mesons exist only because of uncertainty principle for very short times. Absorption of neutrons by nuclei. The existence of strong force and the manner in which it functions makes it clear why neutrons are so suited to bombard nuclei. A neutron does not feel the Coulomb force, it is a neutral particle, and can penetrate the target nucleus. Since it does not feel any force, any Coulomb force, it can go inside, it can penetrate the nucleus. When it comes close to other nucleons within a Fermi 10 to the minus 15 meters, it feels the strong force. It becomes a part of the target nucleus, an isotope of the target nucleus is formed. If a neutron is coming and there is a nucleus here, then it can penetrate, but once the poor fellow goes inside, it feels the strong force, so cannot come out. So, the neutron is therefore absorbed by the nucleus, and what happens? The mass number of the nucleus increases by 1. That means, it becomes an isotope of the nucleus. We shall see a few reactions in which this happens. One of them is this: calcium, which has atomic mass 40, mass number 40 and the atomic number 20, it can absorb a neutron and it can become the isotope of calcium with mass number 41. In fact, absorption of neutrons one by one is the process by which heavy elements are built in the universe. The process called nucleosynthesis takes place inside the stars. You see, inside the stars there is fusion up to building up to iron. Iron is the most stable nucleus, therefore, there is no fusion beyond iron. Then the process of absorption of neutrons starts. The nuclei absorb neutrons one by one and build heavier particles. This process is called nucleosynthesis. Nuclei with the same atomic number, but different mass numbers are called isotopes. So, this one is isotope of calcium. If the product nucleus is a neutron capture process, is an excited state. You see, most of the time when neutron is captured, the product nucleus or the daughter nucleus, this is known as parent nucleus, this is known as daughter nucleus, is usually left in an excited state, and then it comes back to the ground state by emitting a gamma particle. Remember, in an atom, electron comes back to the ground state by emitting a photon of energy which is much smaller than this energy. In the case of nucleus, the gamma particle is emitted once the excited nucleus comes down to the ground state. Now, the gold Au 198 with atomic number 79 can also decay. I told you that if there are large number of nucleons present in a nucleus, then the nucleus tends to be unstable. So, this gold nucleus 198, this is unstable, therefore, it decays by emitting a beta particle, and this is the equation. It becomes mercury 198 80 with the emission of an electron and an antineutrino. And since it emits an electron, one more positive charge, one more, so to say, neutron has been converted into a proton, and therefore, the atomic number of the daughter nucleus increases by 1. Another example of neutron capture is the fission reaction. You see here, this is uranium 235. I think you are familiar with this. With atomic number 92, it absorbs a neutron. This becomes 236 uranium with atomic number 92, which emits now 2 neutrons plus 2 nuclei, krypton and barium, and also lot of energy. You see, and you can see in this equation, I shall deal with it also later, that the number of nucleons is conserved as well as the charge is conserved. You see, 56 plus 36 is 92 is conserved, and then here you can see 1 neutron becomes, and 235 becomes 236, emits 2 neutrons. So, this plus this should be 234, which it is 92 plus 142 is 234. And lot of energy is emitted. Where does this energy come from? We shall discuss it later. So, at the present time, our understanding is that all fundamental forces act through the exchange of particles. In particular, the Coulomb force is created by the exchange of photons. Photons, you are familiar. Like exchange mesons, the exchange photons are also virtual photons. The charges participating in the reaction continuously emit and absorb them. The role is to transfer force momentum between the charges. I tried to picture this. These are the 2 particles, and these are virtual photons in between. They emitted, absorbed, and they can exchange momentum between them. This is the consequence, and this is results in the force between these 2. In this lecture, we have discussed the structure of the nucleus. We found that a particle called neutron, which has no charge, is neutral, was discovered, and that helped us in explaining the structure of the nucleus. But the Coulomb force between the protons again posed a problem, and that problem was overcome by the discovery of the strong force which acts between nucleons. And then we also discussed the absorption of neutrons and the emission of beta particles by the nuclei. In the next lecture, we shall continue with this story, and we shall see how the nuclear reactions take place and how the nucleus, the daughter nucleus, is left in an excited state from which it comes down to the ground state by emitting a photon, a gamma particle in this case. We shall also study the size of the nucleus, how big is the nucleus, and we shall see the nuclear stability. I told you already that if there are large number of nucleons present, they tend to make the nucleus unstable. So, we shall worry about nuclear stability, and we shall study emission of alpha beta particles by the nuclei and the scheme by which nucleons decay.